Hi, this is Patel. In this lecture, we are going to see few elastic constant derivations and its examples. We have seen the definitions of this kind of different types of elastic constants in the previous lecture, and also done one of the derivation in the previous lecture. So based on that particular reference, we are going to introduce some more derivations, and based on that we will calculate one example so that you can understand the procedure in the examination. So let's get started with the first slide, and that is nothing but the derivation of the relation between the modulus of elasticity and bulk modulus K. Now modulus of elasticity can be denoted as E and bulk modulus K can be denoted by the K. Okay, so both have been introduced and defined in the previous lectures. So in this lecture we are going to establish the relationship between them, and for that relationship we have considered one block, as you can see in this diagram, and which is subjected to the equal intensity of the stress in the three mutually perpendicular direction. As you can see in this diagram, the block is subjected in a x, y and z, x, y and z, three mutual perpendicular direction stresses, but each stresses are nothing but of equal intensity. So we will consider the value of the stress and denote it as a sigma. The block points or the end points or the corner points of the blocks are represented by the A, B, C, D, E, F, G, H. Okay, so those are the corner points of the block, just to identify the plane on which we have applied the different types of the stresses. Okay, so consider a cube of each side having the length of L, which is subjected to a direct stress of sigma on the faces of the cube. Now consider this initial volume of the cube, which is nothing but the volume of the cube can be written as a L cube. Now V equals to L cube. Using the previous method using which we have done the previous derivation, that is by the differentiation, we are going to find out the change in volume, and due to the direct stress the volume of the cube will change, and in order to find out the change in volume we can write by the differentiation delta V equals to 3L square, that is the differentiation of the L cube into DL. Now the volumetric strain is nothing but the dV by V, that is change in volume upon original volume. So if you put those value from dV and V from the above two equations, then you can write it as a 3L square dL upon L cube. Now this equation can be simplified by cancelling out the L square from the numerator and denominator L cube. So the rest of the equation after the simplified form can be written as epsilon V or EV is equals to 3 into dL upon L. Now what is dL upon L? dL upon L is nothing but the linear strain, and that can be written as a epsilon L or epsilon X. Okay, so epsilon L into 3 can be written as a epsilon V. This is our volumetric strain, and volumetric strain we have written as a 3 times linear strain. Okay, so now the longitudinal strain or a linear strain of any side of the cube can be written as delta L or dL upon L, and dL upon L due to the three mutual perpendicular stresses, one stress will increase that longitudinal direction dimension, and another two mutually perpendicular stresses are going to decrease its dimension, and that's why the increase can be written as a positive sign and decrease can be written as a negative sign. So in order to write the longitudinal strain of any side of the cube, it can be written as epsilon L equals to delta L upon L, and that is nothing but the sigma upon E minus mu into sigma upon E minus mu into sigma upon E. The first term is along the x direction the last two terms which have the negative signs are along the y and the z direction. Now, if you take out the sigma upon E as a common, then EL equals to sigma upon E into 1 minus 2 mu. So this is our basic equation of the longitudinal strain or a linear strain. Now you can easily find out the volumetric strain by putting this value into the volumetric strain equation. The volumetric strain equation, as you can see, is nothing but the sigma epsilon V equals to 3 times epsilon L. So epsilon V or EV equals to 3 times sigma upon E into 1 minus 2 mu. So these are our basic equation in terms of the volumetric. Okay, so now we will see the rest of the bulk modulus definition. As per the definition of the bulk modulus, K equals to sigma upon EV. This is our definition of bulk modulus. So if you just put down the value of a EV, make it as a subject and put down the value of a EV, then substituting in the equation number 2, you can get the answer sigma by K equals to 3 times sigma upon E into 1 minus 2 mu. Now, sigma by K and 3 sigma, both side sigma is common. So you can easily cancel out in order to simplify this equation. By cancelling it out and making the E as a subject, because we need to establish the relationship between the Young's modulus, so we are making E as a subject. So E equals to 3 times K into 1 minus 2 mu. So this is our basic equation or the basic relationship between the Young's modulus and modulus of bulk modulus. Okay, so this is our final answer of the derivation, and we will conclude our derivation over here. This can be asked in your examination into 5 to 7 marks, and you need to write your answer according to the marks they have given. Now we will see another derivation, that is the derivation of the relation between the modulus of elasticity, modulus of rigidity and bulk modulus. Relation between the 3 basic elastic constants, that is E, G and K. Those are the very important elastic constant, and one should know the relationship between them in order to find out the unknown elastic constants from the known 2 elastic constants. Okay, so we have E equals to 3K 1 minus 2 mu and E equals to 2G into 1 plus mu. So these are the relation which we are already knowing. Now in order to find out the value of the E upon 3 from this equation, E upon 3K equals to 1 minus 2 mu, that is also known. Now what we are going to do is we are going to interchange both the terms from the both side of the equals to. So if you put the 2 mu on the another side, on the front side, then 2 mu will be positive and 1 minus E upon 3K will be the answer, equals to 2 mu. Now in order to find out the mu as a subject, then our answer will be 1 by 2 into 1 minus E upon 3K. So this is our answer of the mu. Okay, from the equation number 1, we will write our equation number 1, that is E equals to 2 into G into 1 plus mu. Now again make a subject mu over here also. So E equals to E upon 2G minus 1 equals to mu. So now again we have represented the mu as a subject from this equation also. Now what we are going to do is we are going to equate those 2 mu from the 2 different relationships. So if you equate those 2 mu, then your answer would look like this. Okay, so first of all we are going to introduce our 2 mu as here equation over here. So 1 upon 2 minus E upon 6K equals to E upon 2G minus 1 plus 1. Okay, minus 1. Now simplify this equation, take this 1 into onto the another side, it will be plus 1, and take this one into the another side, it will be plus. Oh, okay, our final answer would be 3 by 2 equals to, taking 1 by 2 common, our answer will be E upon G equal plus E upon 3K. Now if you simplify this equation further, then we can cancel it out, 2 over here and 2 from here. So our rest of the equation would look like this, that is E equals 3 equals to E into 1 by G plus 1 by 3K. So if you take the LCM from this equation, you can get the answer as a E into 3K plus G upon 3kg. So our final equation, in order to simplify this based on the subject of the E, so our final equation would be 9 kg upon 3k plus G, that is nothing but the E. So we have the E equals to 9 kg upon 3k plus G. That is our answer of the derivation, and this can be asked in your examination into 4 to 5 marks. So you should be prepared for this kind of explanation. Now we will move on to our final slide of this lecture. That is nothing but the example based on those concepts that we have already learned in this lecture and in the previous lecture. So we will see the data which is provided in your examination. That is nothing but the rectangular block is 205 mm long. Its length is 205 mm, 100 mm wide and 80 mm thick. Its width is given as 100 mm and 80 mm thickness is given. Each and every dimensions are represented in the diagram which is provided beside it. So if you consider those dimensions, then you can directly identify the length of the block, the width of the block and the thickness of the block, which is given as which is provided in the dimension. Now it is subjected to a tensile load of 200 kilonewton, compressive load of 300 kilonewton and the tensile load of 250 kilonewton along its length, width and thickness respectively. So what was its length? Its length was 205 mm. Its length was this. So this length is along the horizontal direction. So in the horizontal direction we will represent 200 kilonewton. Okay. In the vertical direction we are having its thickness. So its thickness is 80 mm and that's why the 250 kilonewton load is of compressive nature and which is represented by this. And along its width is 100 mm which is in the Z direction and that's why we are representing 300 kilonewton tensile load in the Z direction like this. Okay, so this was the explanation of the diagram. Now let's see what they are expecting us to find out from this example, that is find the change in the volume of the block and also calculate the shear modulus for the block. And for that particular block they have provided the value of Young's modulus and Poisson's ratio. So these are the given data, and given data is written in this form, that is Px equals to 200 kilonewton, Py equals to minus 300 kilonewton and Pz equals to 250 kilonewton and E is given as in gigapascal. So we have converted it into the megapascal. Now stress in each direction should be found first in the case. Okay, in the first case stress in the each direction should be found. We have the value of the forces in that particular direction and the dimensions of that forces, dimensions of the cross section area is also provided. So we can directly put the equation of the sigma. Sigma is equals to force upon area and the force is Px upon area is B into T, which is perpendicular in the x direction, which is perpendicular to the x direction. So if you put those values in this equation, you can get the answer of the sigma x, which will be in the Newton per mm square. Now, or megapascal. So now similarly we will find the value of sigma y and sigma z. So these are the very basic equations, and from those basic equations we can easily find out the value of the three different stresses so that we can calculate the volumetric strain. Okay, so the volumetric strain equation is nothing but the sigma x plus sigma y plus sigma z upon E. Why we have selected this equation? Because this block is subjected to three mutual perpendicular stresses, and that's why we have to find out the volumetric strain using this equation. And in this equation there is a utilization of the Poisson's ratio, Poisson's ratio is also provided in the given data, so you can directly enter that data from this given data. And we have already calculated the value of the sigma x, sigma y and sigma z. So the volumetric strain, finding the value of the volumetric strain should not be the issue. So you can directly find the volumetric strain as a 4.5 into 10 raised to minus 5. Now this is the unitless quantity. So you do not have to enter any unit over beside it. We will see the change in volume from the volumetric strain in the next step. So change in volume can be represented as a delta V. Delta V is nothing but the epsilon V into V. Now we have the value of epsilon V as we have already calculated as 4.5 into 10 raised to minus 5, just like above. Okay, so delta epsilon V is already given, and V can be written as a LBT, which is the simpler volumetric equation of the rectangular block. Now by the simple multiplication you can calculate the change in volume as a 73.8 mm cube. The dimensions are in mm, and that's why make sure that you are mentioning the correct unit, otherwise your marks can be deducted. Now our last step is to find out the shear modulus. As we all know that the shear modulus can be found out using the equation of the relation between the E, G and mu. So we have the relation as a E equals to 2G into 1 plus mu. You should remember this equation thoroughly so that you can apply whenever it is required in your example. And if you enter the value of the E, which is given in the given data, if you enter the value of the mu, which is also provided in the given data, then the only constant which is unknown from this equation is nothing but the G. So G value can also be found out. Its unit, the unit of the G or the shear modulus will be Newton per mm square. So this was the end of our example, and we will conclude our lecture over here. In the next lecture, we will see the concepts of the center of gravity and moment of inertia and centroid. So till then, thank you.